are coming from the two-port noise MOSFET parameters. We have seen this, the expression for drain current, the expression for gate current, and all these come from unit 1. So the expression for drain current, gate current, and the GG, which is gain, the trans conductance which is present in the expression. So recall that. So we know that the correlation coefficient is defined by ING, I conjugate ND by root of I square NG into I square ND. So correlation means we are going to see how the gate noise and drain noise are correlated. So they say the long channel will have, theoretically it is the J.395. So which means that they are correlated by 40 percentage. The correlation is only 40 percentage. 40% means the some resemblance of gate noise and the drain noise is only similar by 40 percentage. Okay, we are going to see how we can minimize the correlation. Okay, so while the achievable noise figure is affected by CGD, the input impedance is going to be a strong function of CGD, which must be taken into account for designing the input matching. When you design the LNA parameters, you have to consider all these parameters for designing the input output matching networks. So we will take the noise figure expression from the two-port network RN and GU, and YC. YC is going to be the admittance, which is current by voltage. So admittance has two portions, conductance and susceptance. So YC will be equal to GC plus J into BC. So the first two, we are going to see the consider the noise expression using the first two expression what we have seen for the drain and gate, and these two are for any two-port network noise parameters. Okay, so from this you can find what is the voltage in terms of current. So I have IN square, I square ND, I want E square, so I am finding it by dividing by GM square. And because in the expression for Rn I have E square, substitute that, you will get the expression for Rn. So Rn is going to be gamma into GD naught by GM square. So I got the expression for Rn. So, however, because of a noisy drain current force, even the input is open circuited. So you know that gate of a MOSFET is always open because the input impedance is very very high, right? So even though the gate is open, but output current should be zero, right? That is not zero; it is non-zero because of some noise. So definitely under that condition, whatever the current is flowing, that is given by noise current. So I can model that by this equation. So I square n1 equal to this expression. So uh, so this will give a very good approximation for omega t if I am going to minimize the gate resistance. So the input noise current IN1 is quadrature and therefore completely correlated with the input noise voltage EN. So input noise voltage we have found out EN. The input noise current we have found out just now, and they say that both are correlated because they are present at the same site. So the total noise is going to be sum of the noise from the drain plus sum of the noise from the gate. So the total noise will have two expression. So YC is equal to IN1 plus INGC by EN. So IN1 is going to be, see here, it is the input noise current, and INGC is going to be the noise because of gate current divided by EN. So divide each term, you get J omega CGS plus INGC by EN. And when you substitute everything, you get J omega CGS plus GM into INGC by ND. To express YC in a more useful form, I'm going to simplify this so that I'm going to find right in terms of the correlation. So GM into INGC by IND, I can write it as GM into, I am multiplying and dividing by IND conjugate. So even if you cancel out this term, you'll get back the previous thing. So when you multiply and divide by E and D, denominator you will have I square and D, and numerator you will have the correlation coefficient, I N G into I star N G.